Hi guys, welcome back to the channel, and today we will be discussing the problems around the week 6 quiz. So we'll be looking into what is the exact reason that we have selected certain options, and that will also help you out in the coming examination for the NPTEL data design and analysis of algorithm course. So let's look into the first problem. So where the first problem says that we need to find the successor node for the node P. Now, whenever it says that you have to find a successor or a predecessor, most of the times it can be assumed that the problem statement by default says that you have to find the in order successor and in order predecessor. So let's just look into this particular problem, how the answer to this particular problem is H. Okay, so if you see this particular node, we can analyze that to understand what is a pre-order traversal first, sorry, what is an in-order traversal, let's understand first what is an in-order traversal. I hope everyone knows the in-order traversal basically means that we would be going towards the left first, leftmost node first, work on the route. Once the working on the route is done, then we go towards the right. So this is one of the ways to understand what the problem statement actually asks. So we have to do an in-order traversal. Now, the second step is to understand what is a successor, what is known as the successor. Now, successor basically means if you are standing at the node B, right, you have operated on node B, what will be the very next node that would be operated? Right, in other words, we can also say that which route will it be that would be operated at this particular point of time just after node B has been printed. So let's assume that to solve this particular problem, we can do it in a way that we write down, print all the in order traversal and just find what comes after B. Whichever node comes after B, that is supposed to be our answer. Right. But now let's say that you don't want to print the entire node structure. So there is a way, like you can just consider this particular subtree and just go about its traversal and try to find out that which particular node it gonna be that would fetch you the result. So in this particular case, if you look closely, if we start, if let's say B is my root node, so what will happen? You will be first going towards the left node. So left node would be D, and D will be getting printed. Now, as in order traversal says that once you have gone towards the left, you will be coming back to the root. Now the root becomes B, and you will be printing B. Now you will be going towards the root again. So sorry, going towards the right again. And as you go towards the right, you will be finding an E. But this becomes the root for the next subtree. The next subtree being this. So in this subtree, E is the root, and it will also say that go towards the left. So as soon as you will go towards the left, you will find this particular node. That node is H, and that would be actually the answer. Because for B, we can see that for B, the very next node that is coming is nothing but H. So H becomes ideally our answer. Okay, so now let's look into the very second problem. The second problem says that we have n distinct values stored in the binary search tree. Perfect. So we have given a tree that is a binary search tree and has n distinct nodes. Define the height of a tree to be the number of nodes in the longest path from root to leaf. So it's basically a definition of a height. Height is nothing but the longest path from the root to the leaf. So that becomes ideally the height of the tree. So we have to tell which of the following statement is not true. So let's look into the very first statement, if that is true or not. If the root is median value, the height of the tree is at most n by 2. So this case is actually possible if we consider this particular case. So let's say we have number of nodes like this. So 1, 2, 3, 4, 5, and this is the sixth node. Right. So if you were given a tree, something like this. So it is possible that having n is equals to 6, you are having height n by 2, that is 3, and this is actually your height. So this statement is true for itself. Right, let's look into the second option that is given to us. Okay, so the second option says that, let's look into the third problem because that is a negation part. The height of the tree is at least log n. So this is actually possible in case you are given a complete binary tree. Now, what is a complete binary tree? Complete binary tree is a something that has all its children completely free, right? If all the children are free, then you can always say that the height would be in the order of log n. So let's look into that. So this is one of the trees with height is equals to 3. Now let's try to prove this thing. So can we say that number of nodes at this particular level is 2 raised to power 0, number of nodes at this level is 2 raised to the power 1, number of nodes at this level is 2 raised to the power 3, and so on. If we continue, the number of nodes are gonna increase subsequently, and if the height is h, so at the very last level, total number of nodes will be 2 raised to the power h minus 1. So if we say that 2 raised to the power 0 plus 2 raised to the power 1 plus 2 raised to the power 2 plus so on plus 2 raised to the power h minus 1 is equals to n, that is total number of nodes. These will be the total number of nodes. If you see this very closely, this is nothing but a GP. And if you find the sum of GP, it will turn out to be the sum is 2 raised to the power h minus 1. And this is nothing but equal to n that is given to us. If we do 2 raised to the power h is equals to, if we solve it further, then we can say that this would become something like this and log of n plus 1. So if we consider n to be a very large value, so plus 1 could be neglected out. So in turn, we can say that h would be nothing but equal to log n. Hence, the height can be equal to log n, and hence the third option is also true. So the third option says that the height of the tree is at least log n. So yes, at least it can be log n. This is possible. We have already seen. Now let's also look into the very third problem, the fourth statement. The fourth statement says that the height of the tree is at most n. Now this is also possible if we consider the tree to be skewed. Now what is a skewed tree? A skewed tree is nothing but having all the uh okay, just a second, but having all the nodes at just one side, right? So in this particular case, if you consider this as node 1, node 2, node 3, node 4, node 5, node 6, node 7. So height is 7, number of nodes is also 7. Now why height is 7? Because this is the longest path from root to the very leaf node, right? So in this particular case, height will definitely be equal to the number of nodes. Hence, the option D is also true. And let's analyze why this option is wrong. This option says that the height of the tree is at most log n, which is not true because over here we have already seen the height of the tree can be at most equal to n and not log n. And hence, the option 2 is wrong. Hence, our answer also. Moving further, we have another problem that says that suppose we have some values stored in a binary search tree of height n, right? Which of the following statement is true? Now, the number of elements in the tree is at most n. Now, we have just seen this example wherein we talked about a skewed tree. Now, the height would definitely be equal to n at this particular case only, and all other cases will not hold true. Now, it says that at least n. No, at least n is not possible. At most n. Always keep in mind the maximum and the minimum. Minimum can be definitely log n, but minimum n is not a valid statement. Okay, the third option says that the number of elements in the tree is 2 raised to the power n. So this is again not possible because total number of elements in a complete binary tree can be maximum up to 2 raised to the power n minus 1. Hence, this option also stands false. The third option says that number of elements in the tree is at most n log n. So n log n is not possible at any case, because the maximum number of elements that are possible is n at most. That is also possible in a skewed binary tree only. Moving further, we have this particular statement which says that we are given a pre-order traversal. Now, what is a pre-order traversal? Pre-order traversal is something wherein we process root first, we then further recursively call on the left subtree and towards the right subtree, and then finally compute our answer as required by the problem. Okay, so we need to tell which of the following statements holds true. So in this particular case, if you analyze order of log n, if the tree is balanced, otherwise it will be n square. Order of log n, if tree is balanced, this is not a valid case, because let's say we are given a tree that somewhat looks like this. Now, log n says that you are at most going towards the level of height only. You will be traversing only 3 nodes. That is not something we call a pre-order traversal. Pre-order traversal is something. Now, traversal as a word itself says that you have to traverse all the nodes, right? If you have to travel all the nodes, n square, I can understand, because yes, there can be a confusion with n square, that we are making a 2 recursive calls, and the 2 recursive calls, the compute might go up till n square, but again, that is also not possible. Whenever we have to deal with questions on time complexity, always see how many times you are traversing a particular node. In this particular case, you will be at most visiting each node at least once, and if that happens, the maximum time complexity for this problem can be only order of n, and it cannot go beyond that at any particular case. So hence, option D is always true, that whether the tree is balanced or unbalanced doesn't matter, the order will be always n. Now, the fifth question is actually very interesting. It sounds very interesting to me. And it says that you are given a pre-order traversal of a binary tree with integer value produced in the following sequence, and you need to tell that what will be right child of the root of the tree. Right, now let's first understand what this particular statement says. Right, let me just take these values. Okay, so if we look at this particular problem, so we are given these values and we have to compute the pre-order traversal of the binary search tree and find out what is the right child of it. Okay, so let's first understand again what is a pre-order traversal. Pre-order traversal is nothing but working on root first, then going towards the left, and then further going towards the right. Again, another catch is that it is a BST. So if it is a BST, root, and this is left, and this is right. So if a particular value x is being denoted at root, so all the values that are less than x would be coming here. So all the values that are less than x would be at the left, and all the values that are greater than x would be coming towards the right. So having this idea in our mind, we can say that the first value that is between 35, 23, 26, 46, 40, 39, and 41, the first value is definitely going to be the root value. So we can make a call that 35 is my root value. Now, if your 35 is your left value, you need to make a decision that how many values will be on the left and will be on the right. Right. So the assumption that we made, that all the values that are lesser than 35, lesser than the root, will be on the left, and all the values that are greater than 35 will be on the right part. Again, let's see how many values are less than 35. That's 23 and 26. How many values are greater than 35? That is 46, 40, 39, and 41. Now we need to tell the right child. So let's not bother about what is happening on the left. Let's understand what will be the root in this particular case. Now, doesn't that make sense? The first value would be the root value. Why? Because we are given in the question that you are always working on the pre-order traversal and there's a BST. So definitely 46 is going to be your right child of 35, as in this particular subset, 46, 40, 39, and 41, you are getting 46 as the root value. So with that, we are done with the explanation part, and more of such videos will be coming soon. Thank you so much for your support and stay tuned to the channel. If you like the content, please do share, do like our channel, do like this video, and do comment down below that what is the next that you actually want us to share. And we would be happy to create such content in the near future too. Thank you so much, guys.